in G. So it is a abelian rule. Is it clear? Last one is clear to everyone? Is
Yes,
last
sir.
clear? Yes. Okay. So this is the simple problem. Similarly, you can get lots of problems. Like this. Now come to the today's topics. Okay. In today's topics, we are going to study today. We are going to study some properties of groups. Okay. Or some theorems on group. Okay. So first, uh, if sorry, if G star is okay is a group and suppose we consider the A, B, C belongs to G, okay, then A star is B, this is equal to, and A star is C, this implies B is equal to C. It is the left cancellation laws. So if G holds, if G is a group, then left cancellation law must hold. And similarly, if we have a B star is A and this is equal to C star is K, if these two are set, then this must be, there must be B equals to C. That means it is a uh, left cancellation law, and this is the right cancellation law. Is it? So this cancellation law is very important. That means if G is a group, then definitely cancellation law holds. Okay, and based on these theorems, we are going to prove many problems. So first, how to prove this one? You see here. Proof is very simple. Okay, you say ABC belongs to G. Okay, so ABC belongs to G. You see here, A belongs to G. This implies, and G is a group. Then its inverse minus A, denoted by minus A, that also belongs to G. Is it clear? Since A belongs to G, that means its inverse. G is a group, so definitely each element has inverse in itself. So A has a inverse denoted by A inverse denoted belongs to G also. Now, what's the given? We are going to prove this one first. Given A star is B, this is equal to A star is. How to cancel out this one? Very basic idea. Multiply. We should not write the multiply, we should write the operate. Okay, multiply both sides by A inverse. Okay, why I am using this multiply notation? Because once this is understood, then generally we are denoted this by AB equal to AC implies B equal to C. Okay, so we are not just depict the asterisk sign over here. Okay, whatever may be the binary operation that is applicable over here. Okay, simply we write AB equal to AC, and it is like a multiplication. That's why I am writing here multiplication, but exactly not multiplication. Multiplication not, whatever the binary operations given over here, that is applicable to here. So you may write multiply, pre-multiply. I am writing the pre-multiply. Pre-multiply both sides by A inverse. So what you will get? A inverse star is A star is V, and this side also A inverse. And what is the A inverse? It is the, this is the inverse of A. C. Okay. Now, what we have to do next? Uh, implies you may write A inverse asterisk A. So keep it the property of the group in mind,
Now
and then try to
I think
solve it.
screen is visible to all.
This is A
Yes, it is visible.
Okay. Previous class we have proved some theorems
Which
related to
property
group.
we have
Now
applied over here.
simply come to the semi group. It has also lots of importance in computer science.
Which property of the
semi
group?
group.
Associativity.
Good.
Associativity.
Okay, so what is the semi group? Okay. Algebraic structure. Any algebraic, suppose I am denoted by S.
By association.
S star.
Now,
This is the algebraic
what is this?
structure.
This is the inverse of
algebraic
A.
structure.
So you may write
This
it
is
like
said to be
okay. What is E?
semi group. Okay.
What is E?
Identity element.
This is said to be
Identity element.
semi group.
See,
E. First one.
E being
You see, this is the binary operation. This asterisk is the binary operation. So
identity element.
this must satisfy the closure property.
Now, if you multiply or if this binary operation operated between any elements and the identity elements, it's give the same.
If it satisfies this closure law, what is the closure law? If AB belongs to S, this implies A asterisk B that also belongs to S, and this is for all.
So we start from where? This.
Okay.
This. Free multiplication is there.
And second is the.
So we start from
we are
here.
not considering the last two and associative.
Is it clear? Similarly,
so what is the associative law? A star is
we can prove
B. So if algebraic structure equipped with the binary operations studies satisfies only two conditions. One is the closure and second is the associative. Closure is not so important because we already define the binary operation. In the binary operations, that means it satisfies the closure law if it is the binary operation. So basically,
yes, sir.
If it satisfies the associative law. Okay. So if these two conditions satisfy, then we say that S is the semi group. For example,
the left cancellation law holds.
Example, suppose
okay. Now
set of natural number. Okay. And simple addition.
You can try.
Is it a semi group? Just tell me. This is first question number one. And second question is
theorem is the identity
set of integers. This is the set of positive integer 1, 2, 3, 4, 5, 6, this. And this is set of integers. That means including the negative one as well as 0. And we give a negative minus. So minus is the operator or the binary operation operate on the elements of Z. Okay. Now tell me whether both are semi group.
So both is semi group.
How?
So let's
oh sir, second one may be not a semi group, sir, but first one is semi group.
First one semi group.
I'm writing, okay.
It's a semi group. It is the addition law that associativity holds for the natural numbers. And now if you consider
yes.
this,
and nothing is given.
Suppose I am considering the three elements Z.
And nothing is given. Simply
suppose
instead of A star is B, we should write A. Okay.
No. Suppose I am considering the 2
AB.
and
But
the 5
not the multiplication.
and 6. Suppose this belongs
A
to
and B, we have the
Z.
sign S.
Okay.
If
now
we specify
check
this
it.
asterisk sign, then it's okay.
A star is
Then
B.
you use this.
A star is B star is C.
So don't
is equal to how much?
Multiplication B.
2 minus 5 minus 6. And 1 is the A star is B star is C. So it is the 2 minus 5 minus 6. Now tell me, what are the values?
Suppose
it is minus 3 minus 6.
Minus 9.
Minus 9.
And E dash R 2
and 3.
Three.
It is
3.
so it is not associated. Okay.
Yes, sir.
Okay. Then what?
So you may write that Z minus
belongs
is not
to E
associated.
and E belongs to B. This implies
But
A,
if you are
B
taking the plus, then it will be associated.
belongs to B. Closure property. If you
So
want,
it
then
is
you
not a
write the
semi
steric
group.
mass over here.
Not
This is. So are you comfortable with this? Yes or no?
semi group.
Or shall I write the steric mass?
Yes, sir.
Okay.
So are you comfortable with this?
Yes,
So
sir.
these are the
And
simple
this is the
things
identity
for the
element.
semi group,
So you
and
may write it
we
like
have
A
other
belongs to,
examples. Do you know the modulo functions? Modulo function is very
what do you
important
write?
in computer science. Let us we'll discuss this one. Okay.
And E is the
And
identity. E is the identity.
come to the
This implies
isomorphism. Isomorphism is very important.
AE is equal to A because E is the identity.
Uh,
So A into E is equal to A. Also,
isomorphism.
belongs
Actually,
to
isomorphism is a
and E
mapping.
dash another identity.
Okay. So how to define this one isomorphism?
So
Suppose we
A
consider
into
the
E
two
dash.
subgroups.
Sorry.
Sorry, semi-group. Okay.
A into
How to write?
E dash
Suppose
that is
S
equal to also A.
space.
So what you get? A into E is equal to
These
A.
two are the
A into E dash
semi-group.
is also equal to A. So you
And
can
we-
write it AE is equal to A B dash. Can you write in this form?
semi-group. Okay. Then
Yes, sir.
So from here we
A
can
function.
conclude that E is equal
E
to
equal to E dash.
F
how? Which law we are
defined
going to
from
apply?
S to T. S to
Which
T.
law we
Sir,
have
left
applied?
Okay.
cancellation
S
law.
and T are the non-empty subset,
Identity.
and with the same
No, no, no,
binary
no.
operation,
Acha,
suppose
yes, sir. Left
this algebraic structure and this algebraic structure satisfy associativity. That
Okay.
means they are
So E
semi.
is equal to E dash. Suppose we are
Okay.
considering E and E dash are
Then
the two
this
distinct
function
identity,
F
and later
is
we will show that E is equal to E dash. That means
said to
identity
be
element.
an isomorphism
Identity element in a
isomorphism from S to T
is
from
okay.
S to T, not S to T, algebraic structure from S to T. Okay.
Is it clear?
And better to first take, suppose it is 1.
Yes,
Okay?
sir.
Yes, sir.
S1
I'm
and
going to
S2.
give
First
another
you take
theorem and you have to
different.
prove that one.
So
another
you have
theorem
1
is-
and this is 2.
Write them.
So two different binary operations.
So keep it into the mind.
Okay.
Left
From
cancellation
S
and
to
right
T.
cancellation. Okay.
If
Sometimes
now
we have
important
to keep it in the mind
is
the,
said to be an isomorphism from
associativity
S
also.
asterisk 1 to
Basically,
T
we
asterisk
use
2
inverse
if
identity associativity concept.
it is. That means which
So
one is
theorem
F is
the inverse
1 to 1
the inverse of
is it is 1 to 1 and 1 to 1 from S to T, and important thing is there is a 1 to 1 on tape. This is always 1 to 1 correspondence. Okay.
procedure is same.
So 1 to 1
Suppose
and
B
F
and C
of
are the two distinct inverse of element
A
A.
star is B.
Of course, BC
Okay.
also belongs
F
to B.
operate on the
Then
elements of
AB equal
S.
to E and
That's
AC
gives
is equal to E.
F
And then the
so
same
this is 1.
procedure.
Huh?
AB
Okay.
equal to AC.
F star is
Then apply the left cancellation law. You get
B.
B is equal
So
to
this condition is very important, and it is valid for all AB belongs to for all AB belongs to S. So this is isomorphism. Isomorphism, we define the isomorphism from semigroup to semigroup. Similarly, we can define the isomorphism from any algebraic structure to any algebra. It is not restricted to semigroup only.
how to prove it.
But right now, we consider the two algebraic structure as a semigroups. So S asterisk 1 and T asterisk 2 are the two semigroups. Okay. And if there exists a function f which relates elements of S to elements of T
That also belongs
such that f is 1 to 1 on 2, in fact 1 to 1 on 2
it
this
belongs
would
to
be,
G and the identity
okay,
element D also belongs to G.
and
Now,
it satisfies this,
suppose
okay, then we say that it is
B
F is
C.
isomorphic from S to T.
Are
And for example, suppose I am considering
inverses of C. Okay. Of
For
course, B and
example,
C, B and
suppose
C are the inverse. So then B, C both belongs to
if
B
write down if
such
T,
that
any set, is the set of
A star is to B or
Set
AB
of
equal to
all
how much?
even
If A
integers.
belongs to G and B
Okay.
is the inverse of A, then
And
obviously B
set
and
of all
C also
integers. And
belongs to G. Then what happens? A into B is equal to how much?
then
E. Good. E. Identity element. Also, A star is into its inverse C. That is also equal to identity element E.
and Z is
So therefore,
the set
you
of
may write
integers.
AB is equal to AC or implies B is equal
Integers.
to C. Procedure is same.
Okay. Then so
By
that
left cancellation law. Since G is a group, so left
so
cancellation as
that
well as the right
the
cancellation law
semigroup
holds good for G.
Z plus and
Is it clear? So
T
inverse
plus
is also unique.
are isomorphic.
You are not getting the true inverse of this. Okay. So the next one.
Isomorphic. How to prove this one?
So this
See
two,
carefully.
this
T
one
is the
just,
set of even
just
integers
to
and Z
discuss
is the
same.
set of integers.
Yeah.
Then so that
Now come to the next.
semigroup Z and T are isomorphic to each other.
So
Okay.
everybody try
So
yourself
first,
this.
how to
Okay?
solve it? First
Whatever I am
step.
giving, at least give the
Okay.
idea.
We have 3 or
The
4
inverse
steps
of-
to solve it. First step, define the F. So define
Right, like this. The
F, and we have to show
the
that this
inverse of
F
the
is
product of
isomorphic.
two elements.
Okay.
Or
So F from where? Z to
limit
T.
if
Okay. By
G
Fa is equal to 2A. That means T is
and
the set of even integers, okay, and Z is the set of integers. So we define or we take elements from Z,
of course,
operate
A
this
belong-
element
A
with
belongs
this
to G,
F,
that means AB also
and that
belongs
will result
then what is the
element
inverse
of
of this?
T.
Inverse of this
It is
equal
even.
to B inverse.
Okay,
and
so this is
into A.
this
We should not
construction
write
of
the
the
A
F
inverse
is
into
very
B
important,
inverse.
and now we have to show that
B is
F
a
is
group. It's not abelian.
isomorphic. So how can you show that? So if you can show that it is 1-to-1 correspondence, that means 1-1-1-2, 1-to-1 correspondence, that means
G is a group,
if
not
it is,
abelian.
you see, if S is isomorphic to T, then T is also isomorphic
Whether you
to
write
S.
over here or
So if it is 1-1 correspondence and satisfy this condition, that means we have to show 3 things right now. One is this F is 1-1, second is F is onto, and third these conditions. That means F of A plus B is equal to this. Okay. So once you define this one, so come to the step 2. What is the step 2? Define this.
To say, suppose if A is any element and B is the inverse of A, then that means what? A into B is
So
equal
this
to
is
how
step
much?
1. How to show the isomorphism? Step 2.
So inverse of
so that
AB is equal to this. That means the product of this
F
and
is
this is equal to E.
1-to-1
Let us take that one.
or 1-1. Okay.
Is it clear?
How
If
to show that?
A is the inverse of B.
Now
is the
we are
inverse
considering
of
the
A, then
element
you
of
can
B,
write
and
A
we show that B is the
simply
sorry. There corresponds
here it is
only
given.
one and only one element from Z, which corresponds
Inverse
to
of AB.
B.
See,
Okay.
inverse-
So assume, sorry, T,
Inverse
and
of
we
the
consider
AB
that as a B.
belongs to G.
Assume
Is
that
inverse
B
inverse. And this is also belongs to
is a
So inverse
is
of AB
an even integer.
is
I'm writing.
this.
Okay.
That
That means
means
belongs to this
you may write AB
integers. Okay. Then
into its inverse of this.
B
So
is equal to
into
2A,
its
A
inverse.
bearing any integer,
B inverse A
or
inverse.
implies A
If
is equal to
you can
B by
prove this one.
2.
AB into
Now you operate.
this. Inverse of AB is this. Here you have to prove this one. What is the meaning of
FA.
this?
FA will be how
This
much?
is inverse of AB
FA will
is
be
equal
F
to this.
B
So,
by 2, and that is equal
or
to 2 times
equivalently
B
you
by
can
2,
say
and this is equal to
AB
B.
into B
So what is
inverse
the
of
meaning
B
of
is
this?
equal to E, and this
To
is
each
equal to
element
how
A,
much?
we have a
B
unique
is equal
element
to
in
B
to each
inverse
element A in
inverse
S,
into AB.
Z, we have a
And that
unique
is also
element
equal to
in B, and we have already
If
considered
you can
B as
prove
the
this one,
even
then
integer from here. So therefore
ultimately
F is on 1 1.
okay. So let's try it. Everybody try this one.
1 to 1.
I've
Step
already
3.
given you the hint. Everybody try this one.
Sorry, we have proved that on to. Sorry, it is 1 not 1 1. It is on to. 1 1 now. 1 1. 1 1, that means.
Everybody try this one.
What is the meaning of 1 1? If we are considering the two different image, then pre-images are also different. So what you
Slow and
do?
steady.
Let so
Try
that
to prove it.
F is 1 1.
Can we do like A
So how
into
to check
A
it?
inverse?
Suppose
So are
let
you get this one? AB into B inverse into A inverse.
we
is
have the
equal
two
to E.
elements. Suppose F
Are you getting?
A1 equal to F A2.
Yes, yes,
So if these
I'm
two are
doing
equals,
A
then
into
A1 is
A
also
inverse.
equal to A2. This is
Then
the
A
method
into
to show this. So implies twice
This is equal
A1
to E.
is
No.
equal to twice
We
A2,
have to
and
prove this
implies
one.
A1 is
So
equal
what
to
is the
A2.
meaning of
So
this?
this is the,
Meaning of
if
this
two images are
is
same,
AB
then
into
the
B
pre-images are
inverse
also
A inverse.
same. This is the
That is
condition
equal
for
to
the
E.
this is the proof
And
of
also
1 to
this
1.
must be
Okay,
equal to B
so
inverse
it is
A
1 to 1.
inverse
F is
into AB. So we have to
1
prove
1.
this one. If you are getting
And
this
this is
one,
the
that
procedure
means
to 1 to.
from the
That means in
definition of the
1 to what we
inverse,
will do? We consider a element from the
we have to prove this.
codomains. Okay, and then
So how
we
to
have to
prove
show
this?
that
You see,
to each element of the domains,
uh,
that elements becomes the
A,
that means that element of the codomains
B
becomes the
belongs
image
to-
of the element of the
okay.
domain. So
And
this is the way to check the
let
functions to be onto.
A inverse
And fourth step is to last one.
and B inverse
Step 4. So
R.
what you do?
Inverse
We are
B
considering the
inverse.
two elements A F star is B, that means plus, and you see here what is this? Here A star is 1, A star is 2. In our case both are same. A star is 1 and A star is 2 are same, and that is the plus. So A plus B, and we have to show that FA plus FB. So let us
Then
see.
what will
If A plus B is equal to
inverse
how much? 2
that is
times
equal to A
A
inverse
plus B, and that is equal to 2A plus 2B, and this equals to 2A equal to how much? FA
E
plus FB. So this condition is also satisfied. So all the four conditions satisfied. Therefore, F is an isomorphic image or is isomorphism
and B into B inverse
from
is equal to B
you may write Z to T.
now.
So
we have to prove
isomorphism,
this.
that means isomorphism, that means if we have the two algebraic structure which are semi-group S and T with different binary operation, star
And
is
now I am
1
not
and
going
star
to,
is 2,
uh,
such that we have a functions
using the
from S
property
to T
or,
which is 1 1
describing
on
the
2
property here.
and satisfy these
Tell me what
conditions.
property
That
here
means
I
F of
am
A
suppose
first binary operations to B, that is equal to FA
into
second binary operations to this. So this F,
here I am using
this
property
first one
associativity.
is from S, and the second binary operation
Again
if
associativity
star is 2 belongs to
A
this T. So
into
this, so we have to check that some algebraic
again
form,
here
it is
I am
applicable
using
to
the
all,
associativity.
whether
First
it
we
is the
using
semi group
associativity
or
law
group
over
or
this.
ring or
Then
query
we using
or vector space,
associativity
whatever
law
it may
over
be.
this.
If once it
B
is
into B
decided
inverse
that
is equal
it is
to
a
E.
group or
So
semi
we
group,
write it like
then to
A
check that they are isomorphic,
into
that
E
means we
into
have to find
A
a function
inverse
f. which is 1 to 1
you may
as well as the
consider
1 to, and as well as it satisfy the conditions, this
any
last
one of them.
conditions.
You can put it
Okay,
like
this last condition. If it satisfies this, then we say
so.
that
Now
it
what
is
you will get?
isomorphic.
A into
Okay.
E into N inverse. This is A inverse.
Is it
and
clear to
again
everybody?
this is equal to
Yes, sir.
Yes, sir.
Now
Yes,
come
sir.
to subgroup. Okay.
Yes, sir.
Or the
Next, right.
product of the group. First we come product of a group, and later we will discuss the quotient group. Okay. In your book it is written the quotient of groups, but it is not true. This should be quotient group.
B
Okay.
inverse.
So now come to the product of groups or the product group. Product of
In both
Okay.
steps we
So
have
if
associated.
suppose we have a G1
Implies
ester is 1 and
B into B, of course B into
G2
B,
ester is 2
B inverse B.
are
So what you see here?
two groups.
So therefore we see here AB into
Okay, then
B inverse A inverse. This equals to E and again it is
Cartesian
equal to
product given by
inverse
G1
A into B.
cross G2. Okay,
So therefore
or you may
write
this is also a group, that is
the inverse of
G,
AB
and
is
here I am writing the
equal to
ester is. Okay,
inverse
it is ester is 1, it is 2, and it is simply 0. Okay, is a group.
So whenever you have to prove this one,
With
okay, and all the proofs are very simple.
binary
You have
operation.
to keep it into the mind. What are the properties of the group? So group has the four
What
properties.
is the binary operation?
Since
This.
it is the 4 in fact 3 properties.
It's a group
Since,
G
group
with the
is
binary
any
operations
set,
ester is.
if G is a group,
Okay.
definitely it is equipped
Now,
with some binary
how to
operations.
define this
Okay.
ester is
And binary
defined by,
operations are
you see,
associated.
what are the elements of
Sorry,
G?
closed. So
It is the
every group
Cartesian product. So
closure
if
property
A belongs
for
to
all.
this and B
Second,
belongs to this,
associativity,
then
existence of
AB belongs to
identity and
G.
existence
So
of
this
inverse.
G is the ordered
These
pair.
four conditions.
This G is
Okay.
the ordered
And
pair, not a single element.
out of this
So
group,
first we consider,
okay, we have
so
one more property.
G consists of
that
the
is
ordered pair. So
cancellation
we
law.
have to take the two
The
elements from G.
cancellation law.
So what are that
holds
elements?
good for
Suppose
a group.
A1 and B1. This is the one element of this G, because G
In
is
many
the
groups,
Cartesian
we
product of the
use
two sets.
cancellation law
Okay,
to prove the theorem. Okay.
and
Next, you try one more
this
theorem.
element of G
But everybody
connected
has to
with the
prove
another
this one
element A2G
individually.
B2
Do yourself.
by
Otherwise,
these binary operations defined
if some
as
other proof will given in the examination, you can't prove.
this A1
So,
ester is A2
not understanding the method of the proof
and
how to prove
B1 ester
So,
is B2. You see, this definition is completely valid over here. You see,
right.
this
Or
A1
you
belongs
may
to
write like
G,
this,
G1,
or
and this
every
B1 belongs to G2. A2 belongs to G1 and
or
B2
every
belongs to
element A,
G2.
suppose, any
Okay, so and
belongs
this
to, or
A1 ester is A2. Of
or
course,
every
this belongs
element
to.
A belongs to
Sorry, here we have one because, and this is 2.
prove that
This 2. So A1 and A2 are the elements of G1, and since
the
G1
inverse
is
of
a group
P,
with
that is
binary operation ester is 1, so A1 ester is A2 also. This also belongs to G1, and this also belongs to G2. So when you take the cross product of G1 G2, that construct the G, that means these elements are the elements of Z.
Okay, sir.
Is it clear
Try to
what I am
prove
saying?
this.
Sir, please repeat once more.
You see,
You see, there is a similarity
A1,
of
A1,
this one to the
B1.
previous one.
Let me, you see, A1, B1. This belongs to G with binary operations ester is. Similarly, A2, B2, this belongs to G and that also belongs to, sorry, A1 and this A2 I am considering, A1 and A2. This belongs to G1 and B1 and B1 and B2, G2. So you see here, how we define G is defined as the G1 cross G2. Okay, just keep it into the mind, G1. Then if you are considering A1, so we need to correction over here. G1 cross
So we
G2.
can
G1
start
cross G2
like
means
A inverse
G1
A equal to E,
has a
then we
single
can
element,
multiply
G2 has
that
also a
both
single
sides.
element. But when you consider this, this is the product of this is the product sign. So when you take the Cartesian product of these two, so that give a element and the properties or the characteristics of that element is it is always an ordered pair like CD.
We multiply
This is.
AB by this.
Where C
Here we
belongs
need
to
prove the inverse
G1
of this is-
and D belongs
we
to
have to start with
G2. So the elements of, although the elements of G1 and
inverse A.
G2 are a single element, but the elements of G is always a ordered pair.
Sir,
Okay, first
A
thing.
multiply A inverse
Now,
A on both
leave
Anna,
it, these
listen
two things.
carefully. Think about this for 5 minutes. Okay, you need to modify something over here, and then try to prove this. Otherwise, I will prove it.
Now,
In the fifth
G1.
point,
So now we
think
consider
about
the
this,
two
make some
elements.
modifications over here.
This element and this both belongs to G. This also belongs to G and this also belongs to G. Okay, and these two elements connected with the binary operation asterisk. Okay, now how to define the product? G1 equipped with asterisk 1 and G2 equipped with asterisk 2. Okay, and the Cartesian product of this, again it's construct a set of ordered
A
pair.
belongs to G.
This
then
set
prove
of
that the
ordered
inverse
pair
of the inverse
is
of A is
also a group denoted
Here,
by G
So
is
then
equipped
A
with
inverse is
the
also belongs
binary
to
operation only asterisk.
Of course.
Okay. Now question is how you define that.
and so
How you define this binary operation so that this G becomes a group. So this is the way. Take the elements from G, first element from G to G. Take the binary operations between these two. Okay, and that is equal to A1 asterisk 1. That means A1 and A2 both are the elements of Z.
G1.
A1 and A2. So G1.
See this.
And B1, you see B1
A
cross,
belongs to
taking the cross product. So second one is B1 and here the second one is B2. So this belongs to Z2.
Now,
Okay. So this belongs to G1 and this belongs to G2. So when you take the Cartesian product of these two,
see,
then again these
And,
elements belongs to
if
G1,
this
these
belongs
elements
to
belongs to
A inverse
G2. So
belongs
you
to
are
G,
getting a
okay?
element like
Then inverse of A
CD.
inverse
And
also
this is
belongs
the
to-
elements of G.
okay, and this
So
implies
under
that the
these
inverse
binary
of A
operations,
inverse also-
under these asterisk binary definitions defined by this,
and we have to prove that this is equal to this. We have to prove.
okay,
A belongs to
Yes, sir.
G. This implies
Defined by
A inverse
this,
also belongs to G.
we
And
can,
if A inverse belongs to
so
G, then the inverse
it
of
is
this
possible.
denoted
It is
by
possible
this
to show that this G also,
So
G is
now,
also
what we see?
become a group if you are considering this
Uh,
binary operation. This is the
Therefore, you may
product
write it
of the two
A inverse
group.
into
Okay.
you may write
Now,
the inverse of A
very
inverse.
easily you can prove
That
this
is
one.
equal to
You see, here from this you see that it is a
and we need to prove
closer
equal to
because
A.
if it is the elements of G,
pre-multiply
it is
by
the it is also elements of G. Then this is the element of G1, this is the element of
multiply
G2,
by
and the Cartesian product of these
Okay.
two belongs
what
to
will
G.
get?
So it is a closed. Important thing
A,
is the
that
associativity
is A
and the
inverse
inverse. So how to
and
check the
that is
associativity?
inverse of A inverse, that is equal to A asterisk E.
So make it practice how to
Use the associativity
prove
property.
the
You may
different
write it
properties
A
of the
A
algebraic
inverse
structures. Presently we have only group.
inverse of
Okay, that group, that means definitely it is the closed. We have to show that. Along with this, we have to show that it is associative. There exists identity as well as the inverse also.
Inverse of
So
A
now
inverse
you take
is equal to A.
elements A. Suppose let
A
A,
inverse of inverse.
B and C all belongs to G. So you see here I am taking A, B, C. It doesn't mean that these are the single elements.
Okay. That's good.
Actually, A is the form of suppose A1, A2 like this. B is the form of B1, B2. Okay.
Okay, let us
So
prove, one
then,
but
or
you see there are
we may write
been
it
a number of
like
proofs
this,
related to this.
where
So why we are solving this case?
A
This is
is
for practice.
A1, A2,
You should understand
B,
how to prove the third theorem.
B1, B2, and that of
Keep it
C,
into the mind that we have only four
C1,
properties.
C2. This.
Associativity,
So now just check it. A star is
existence of
B
identity,
star is
existence of inverse,
C.
and cancellation.
Now prove it. Everybody
These four
try to.
properties we have.
Okay.
And using
So
these
instead
four
of A, I am writing the
we
A1,
have
A2,
to prove any theorem
and this star is
related to this
B1,
group primarily.
B2,
Okay.
and star is
Sometimes we have to
C1,
pre-multiply, sometimes we have to post-multiply, depending upon
this
the
one,
nature of the problem.
and this is. Now, since binary operation is defined like this, by this, so this can be written as how much?
Sorry, not proof, theorem.
Keep it as usual, A1, A2,
Theorem
okay,
means if G
star is, and how much it is? B1, so this
G
associated with this,
is
okay,
a group
so we may write it like the B1 and C1.
with
So B1 star is, and this B1 and C1 are the elements of G1. So we write it
let
star is 1,
write down the let
and it is C1, and
let
B2,
is a group
and these are the elements of G2, and so I am using the star is
identity
C2.
member
Star is 2 over here.
E
This,
and
now again you apply this one
let.
over this. So how much you are getting? A1,
Then
star is 1, this and this. Okay.
for
So
all
this is the element of G1, this is the element of G1. So A1 star is 1, and we have B1 star is 1, C1. This is the one element, and the second element is A2
and for all
star
A
is 2. These are the elements of G2, and this is B2 star is
if
2,
A
C2.
is square,
And
square,
now-
that means A into A.
Okay.
Okay, or you may write A star
Is it clear?
whatever, this is equal to E.
Up to this, is it clear or not?
Then
कुछ बोलना होगा, yes or no?
Yes, sir.
Yes, sir.
Now this is the element of G1 or G2?
commutative
G1.
property must hold.
G1.
If this-
And G1 is a group or not?
Okay, that means
Is G1 group?
A
Yes,
stress
G1 is group. If it is a
Each
group, then
element-
associativity
each
must,
element
associative law must hold
is inverse
for
of
G1.
itself.
So apply here the associative law. So what is the associative law?
Everywhere.
A1 star
How
is
to
1 B1.
How to prove this? Abelian, that means what we have to
So
prove?
these are easy, but you need some practice.
Sir,
So,
A, B equal to
C1.
B.
We
Okay.
have to prove. Right.
And
So primarily
this side
we
you
have
are
to
getting A2 star is
we have
2
to prove
B2
what?
and star
A
is
is equal to A
2
inverse.
C2 by associative law.
A into A is, you see,
Okay.
A into B
Now
is
break it.
equal to E.
Now at this
Then B
stage
is the
you may
inverse
leave
of
it,
A.
and then again you
But
start
here
from A star is B under
A
bracket, and then
into
star is C, and you
A
will reach
inverse
to
is equal to
this.
E. That
Otherwise
means,
you
and
may
this
write
A
it
is
in this
equal to
form.
this. So both are same.
This
That
is
means
star
we
is
have to
1.
prove that A is
Okay.
A is
Or
A
you may
star
write it
is
like this.
A inverse. This is equal to E, and here
A1
A
star is
into
1,
A is equal to E. That means we
B1
have to prove that A
and
inverse is equal to this
this one.
Is it?
A2 star is 2.
A square E.
B2.
That means A star is K is
And,
equal to E. If A is the any element, then its
here
inverse
you
is given
write
by
the
A
star is
inverse. And if A inverse is
C1
the inverse of A, then the product of these two
sorry,
must be
C1
from these two. We conclude that we have to prove that
simply in the reverse way I am writing over here.
Well,
This.
so ultimately our
Okay.
goal is to prove this. This is the
And
base.
then
Once
you
you
can write it
understand
like
this one,
this.
then proceed. With these conditions, we have to prove this. Okay.
A1, A2
With this condition,
and asterisk B1,
condition
B2.
is this. We have to prove this. So let us start with
Okay.
this.
And from on the reverse way.
So we have to prove this. So
A1, A2 and this asterisk
given A
C1,
asterisk A is
C2.
equal to
From the basic definition. Actually, we
Then
have
how
defined
can you
this.
get it? A inverse. You see, right hand side we
Actually,
have
from
E.
we came
Then
from
how
here
can
to
you get it? A inverse. Either you
okay,
we
and this is
multiply or
nothing
cross
but the
multiply.
A asterisk B and asterisk C. So what we see
We
here,
multiply both
A asterisk B asterisk
by
C. This is equal to this. So it is a
so what you
associated.
get? This is A asterisk A.
Identity.
asterisk A.
How to define the
This is-
identity?
Sorry.
You see.
If you are
Identity
writing the
element.
post, no problem. A inverse.
So how to find the identity? Suppose U1 belongs to G1 and E2 that belongs to G2.
Apply the associativity
Okay?
law. This side
Or
you are getting the A inverse asterisk
identities.
and this asterisk A is equal to A inverse
Identities
implies E
of
A
G1 and
implies
G2. Identity element in fact G2 respectively. Okay. Then we define E is equal to E1 E2. Okay. Define or then
okay. Now
then
if you are considering
is the
any element
identity
we have to prove this one. Next, what we have to
E1
prove
E2 is
it
the identity of
what will you do? It is the element.
G is equal to G1 cross
It is the first condition.
G2. Okay. So
Second, we have to
we
prove that it is
consider
the
this
element.
one.
So what you do?
And
Now
what is
suppose,
this? E1 comma E2. It is your ordered pair. Now we
A-
have to show that
sorry, AB belongs
you are considering this as the
to G.
identity.
Therefore,
Then
A asterisk B. This is equal to how much? A is equal to A inverse.
asterisk E.
So
This equals to how much?
asterisk B inverse.
A1
this is
A2
equal to how much? B asterisk
asterisk
A inverse.
E1 E2.
Okay. So what
Now
is the meaning
define
of
this one. A1 asterisk
implies
1
inverse of this
E1
is equal to this.
and
Therefore,
A2 asterisk 2
is
E2.
equal to this.
Okay. And since E1 is the identity of G1,
clear?
so this is nothing but A1
AB
and
is
this is
equal
E2
to
is the identity
this
of A2,
inverse.
so it is the A2 and this is
equal to this. that
So what you see?
must be whole.
A asterisk E is equal to A. Similarly, you can show that E asterisk A is also A.
Yes, sir.
Okay, that means this is the identity. So how can you show that inverse?
Is it clear?
You take the inverse
A
as
is equal
I'm
to
writing
A.
over here.
So AB
Okay.
belongs to G, the A and B belongs to
Inverse.
G, that means AB also belongs
So
to G.
you take the inverse
Okay.
like this.
And ultimately we are getting the A space B equal to
A1
B space
A2
A
inverse and that is
But we
equal
see
to
that if
A1
it
inverse
is,
and
this
A2
condition A square equal to E holds, then this holds.
So
And
if you
since
considering
A
this,
star is
so this
B
is the inverse
or
of
B
each
star is
element.
A, whatever may be, these are
For A,
elements
this is
of
the inverse.
this G.
So how to check it?
Okay. So
That this is the inverse. You take A1 A2
inverse.
into
That
this
means this
A1 A2 asterisk this,
again from this.
and if it comes E, then obviously, and it is easy to prove.
Yes, sir.
So what we see that this product
Sir,
or
can
the
we put
product of the two group, it is also
value
a
of B as A inverse?
group. The product of two group defined
A
by
inverse.
the
Like we are proving a
this binary operation, defined by the binary operation this.
No, it is not clear
Okay,
to me. What is the
this
proof?
also
So when
constitute
we
a
are proving
group.
G as
So
abelian,
what is the important here?
so
Important is
so
to
can we
define
put
the
that B equals to A
uh,
inverse so that we
No.
can
this
prove
binary operations.
No, no, no.
If you are defining
If you are
different
writing
binary
this,
operations, then
A,
G may
it
not
is
be
given.
a group
It is
over
given.
here.
A inverse equal to E. Sorry.
So, okay, time is over. Now, next class we will start the semi-group, sorry,
This is
subgroup
equal to E. It
and
is
the
given.
permutation group. Permutation group is very important.
Okay. So
Okay.
meaning of what
So,
is the meaning
prepared
of
for
this?
this
When you look at the
permutation
inverse,
group and the
this is
subgroups.
E. E is the identity. We have a
Okay.
star is B equal to E.
Okay,
That
sir.
means B is the inverse of A,
Just a
or
minute,
vice
minute.
versa, A is the inverse of
Minute.
B. Okay. So if any
Okay.
element is
Now,
inverse
anybody,
of
if anybody has any query,
in that
then tell
condition
me.
we have A star is A or
Now,
A
are you
square
following
equal
any
to E.
book related to this?
Okay.
Hmm?
So if B is the inverse of A, then A has two inverse.
Anyone?
One is A itself and second is B.
Sir, online
But
resources.
priorly we proved that
Online? So,
inverse
which
of an
book?
element is
Are
B.
you following any book presently?
So B never be an inverse.
Sir, I got a PDF.
PDF of which?
Is it?
Some institute, engineering institute. So B, it means B can be a distant inverse, no?
Yeah.
Okay, if I got
Of
something,
course,
then I will send this to
B
WhatsApp
is
group.
the
Okay.
inverse
Okay,
of
sir.
B itself.